All right, so talking about forces, and recall back that the variables we have, this initial, final, acceleration, our displacement, and time, these five variables we had from the kinematic equations, what we're now going to do is focus on how to get acceleration. So if we can get acceleration, then we can go ahead and use these equations further. But our goal here for the next couple homeworks is to focus on getting acceleration. And then once we have acceleration, we can use the other kinematic equations to figure out motion of the object. And acceleration is going to come from force. So one of Newton's big contributions is he found that the force is equal to mass times acceleration. This is our big new equation, F equals ma, Newton's second law. But before we get to Newton's second law, let me just go through a few quick things here that are in the book. And we're covering 4.1 to 4.4. And in 4.1, they don't introduce F equals ma yet. What they do in 4.1 is they introduce the forces that we'll be talking about. And I think this is something that's really important as they look to the types of forces here, because the real world is complicated, and we're not going to deal with all those complications. And one of the challenges I think with introductory physics is knowing what the forces we are going to be dealing with and what are the ones that we're going to be ignoring. And these are the four forces that we're going to be dealing with here. And I'd actually throw in a fifth one in here, but these are the forces we're going to be dealing with. And when you're thinking of these homeworks, only think of these forces. The world may be more complicated, but we're not going to deal with that. We're only going to deal with the forces that we're talking about here. So the very first one I talk about is the normal force. So the normal force, if I put my pen on my desk, it doesn't fall through the desk. Now the reason that is because on the atomic level, all the electrons and they're all and atoms are all bounded together through the electric forces, and this holds a support system up. And it's actually the electric forces that stop my pen from falling through the table, all the bonding on the atomic level. And there's tons of complication there that we don't deal with. So on the atomic level, all the atoms are bound together into some crystal type structure. That is kind of what material looks like. And then when you put your pen on it, now remember the pen is gigantic compared to atoms, but when you put your pen on it, it rests on all of these forces here. And we do something very simple then, is all these forces we say just results in a normal force that supports our material. So the normal force is a result of all the electric forces that happen on the atomic level. And just to ignore all those complications, we just call any supporting force the normal force. So when I put my pen on my desk, it's the normal force that supports the pen. The normal force is always perpendicular with the surface. So if I have a table and I put my book on a table, the normal force supporting the book is always perpendicular to the table, always perpendicular to it. If I lean against a wall, then the normal force is always perpendicular to the surface. So if I'm leaning against a wall, normal force will be perpendicular to it. Even if I'm leaning and pushing at an angle, the normal force is going to be perpendicular to the surface. And that's the normal force. It's not one of the fundamental forces of nature. The normal force is just the result of all the electric forces at the atomic level holding material together. But that's our first force here that I want to put down that we're going to need. So for our forces that we're going to need, the normal force, it's a supporting force. It's what keeps objects from not falling through material. So, when you drive your car, the normal force from the ground supports your car. You don't fall through the earth. That's the normal force. When you sit in your car on the seat, you don't fall through the seat because all the material of the seat supports you. That gives you a normal force. So normal force. Also notice the picture in the book, they do have a block on an angle. Notice the normal force is coming off perpendicular to the surface. So that means at 90 degrees. And the normal force commonly given is N, usually capital N, but whatever, small n is fine. But that's our first force, the normal force. Whenever there's surface contact, there's a normal force, and the normal force is always perpendicular to the surface. The next one they have listed here is friction, another force we'll be dealing with. And friction always opposes motion. So, if a plane is flying to the right, well, the force, so if that's their velocity, then the force of friction is pointing to the left. Force of friction always opposes motion. So if you're, say, a block on a ramp, well, the block is going to want to slide down. That's the velocity it's going to go. And so that means the force of friction goes against it. The force of friction always opposes motion, and the force of friction is always parallel with the surface. So let me just get another piece of paper here. So if we have a flat surface and I'm going to push this object, well, if the object is going to move this way, then the force of friction opposes that motion. It's parallel with the surface. And remember, the normal force is always perpendicular to the surface. So these are two forces we're talking about. Normal force. Both of these forces happen when you have surface contact. So when you have surface contact, the normal force comes straight out from the surface, and the force of friction is parallel with the surface that opposes motion. And that's another one of our forces. So we got two forces that we'll be dealing with. If we look at this third one is tension. And tension, again, is the result of what happens at the atomic level. Because a rope is made of, I'm just going to make a string of atoms here, even though rope is made of many, many atoms. But our ropes for this level of physics, I always like to say, are magical because they don't stretch at all. They don't have any mass at all, our ropes, and this makes the ropes easier to deal with. You should think of a rope as just something that transmits a force. So the atoms never stretch apart in our ropes. Our atoms don't have any mass in our ropes. Our ropes are considered magical, and that's how you should think of them. You should think of our ropes as magical. All they do is transmit a force from one of its connections to the other end of a connection. It's all our ropes do. And we say the rope then carries tension in it. The tension is what's transmitting that force to the object. And that's our third force they have listed. And the last one they have here is weight. And this one can get, I think, a little bit confusing with people sometimes because this is technically gravity. Gravity is weight. These two get used a lot. You can see looking at the book, it says weight, the pull of gravity. So think of them both ways. You wouldn't feel weight if there wasn't gravity. So your body has mass, but what you feel when you walk around is your weight. If you go away from Earth or away from a gravitational field, you wouldn't feel that weight anymore. So, for instance, I think Mars's gravity is 1/6 of ours, and so if you weigh 120 pounds, then a sixth of that's going to be 20 pounds. You would feel like 20 pounds on Mars. So, imagine that'd be pretty fun. You could probably jump really high, but the truth is, after living on Mars for a couple years at 1/6 the gravity, all your muscles will weaken and you'll feel weaker. And then you'll come back to Earth and you'll barely be able to walk because all your muscles have deteriorated because you don't need them. If you're only carrying 20 pounds of weight, then your body doesn't need to be as strong anymore. So gravity and weight kind of get mixed up. People separate them, I guess, is the mix-up that happens sometimes. Remember, these are the same thing. You wouldn't have weight if it wasn't for gravity. And what is in there is mass. And let me just say this about mass really fast. So mass is different than weight, and we'll get to that in a moment. That's coming up in the book here. Mass is a number that we quantify it with a number. It's a measure of how resistant to motion you are. And that's what mass is. Mass is a measure of how resistant you are to being moved. So, I have my pen here. My pen, not very massive. It's not very resistant to being moved. Not very resistant. But I got this candle here. I know it's pretty hard to see, but the candle, a lot heavier. I mean, I can still move it, obviously, because it's a candle. But something with higher mass is more resistant to motion. So, for instance, I'm on a desk right here. Now, if I try pushing my desk, well, that's going to be really hard because my desk is a lot more massive than my pen is. So mass is a measure of how resistant to motion you are. And more mass means you're more resistant to motion. That means it's harder. Something that's very massive is hard to get moving, and it's also hard to stop because mass is a measure of how resistant to motion you are. And that's overall what mass is. And then weight is what you feel when you're in the gravitational field. So these are the forces. And there is one more I want to add to here that the book does talk about, but they unfortunately don't have in this nice picture here of 4 forces, is that sometimes, let me get a new piece of paper here, sometimes we may be pushing on something. So another force that I'm going to add to this that we're going to see is what I call an applied force, and a lot of other people do too. It's not just my name there, but an applied force. An applied force is when a human gets involved. So, maybe a human, sometimes a book may use other contexts. 121, we just did one where a monkey was pushing a box. So it could be some other conscious life form, but applied force usually means some human or maybe some life form has come in to push on the object or pull on the object. So if a human comes in and pushes on an object, that's what we would tend to call an applied force. And that's the last one I would add on to here. These other 4 are physical interactions, while the applied force tends to come from somebody pushing or trying to pull on a box or some other object. So these are our 5 forces that we'll be looking for in the problems. And just think of these five forces. The world is more complicated, but we're only going to focus on these 5 forces for our homework here. And that's what you're talking about in 4.1. Just getting us set up for the forces we'll be using. And in 4.2, so I'm going with the book's order here. I'm not quite liking their introduction here. So let me just go back, because I started off by saying F equals ma. And the book still hasn't gotten to the statement. That they're still working towards it. But the reason we're talking about forces now is because forces create an acceleration. And then once we have the acceleration, we can use the kinematic equations. And so it all, kind of works together here. We started with the kinematic equations. Now we're going to talk about how we get acceleration. And we get acceleration from the forces. And that's what we're going to be doing now, is we're going to be looking at the forces that are on an object and then asking, what is the acceleration? And something that can happen here is you could add all your forces together, and there is a new symbol here that we're going to be seeing. It's in the book too. It's the math symbol, the summation symbol. Now, physics uses the summation symbol in a very lazy way. It just means sum together. So this means just sum all forces is what that means. And, mathematicians argue a little bit that symbol's not used right, but, it is what it is. It's just used as a word to mean sum all the forces. And if you sum all the forces together, you'll get what the acceleration of the object is. Sometimes this is called the net force or the resultant force. Books sometimes call it different things. So they might also call this the resultant force. And this is what leads to our total acceleration. But what can be tricky here is that if you add all your forces together, it might come out to be zero. So for instance, if I have my book just laying on a table here, well, gravity is pulling it straight down, the force of gravity. There's a surface contact with the table, and so there's a normal force up. Remember, surface contacts are always perpendicular to the surface. So these are my two forces, a book just sitting on a table, gravity pulling it down, the normal force pushing it up. These are the only two forces. And so when we add these forces together, we have the normal forces up, so we'll give it a positive sign. We have the force of gravity is down, and so we'll give that a negative sign. And then what Newton is saying is that when you sum the forces, this does equal mass times acceleration. That's what Newton is saying. The sum of forces is mass times acceleration. However, my book isn't moving up or down. It's just sitting there. So that means the acceleration must be zero because it's just sitting there. And then we get the equation of normal force up, gravity down. Well, that has to equal zero because it's not accelerating. And then we get that these two forces would have to equal. And this is true for something that's just standing still, something that's standing still. But this can also happen for things that are going at constant velocity. And this is the part that messes with people's brains a little bit, because acceleration equals zero can mean two things. Means two things. One means you're not moving. If you have zero acceleration, that means you're not moving. So maybe, you're just sitting in the chair watching this video. Well, you're not moving. I know you might be spinning in your chair, but we'll talk about spinning in the future. Right now, you're not moving. You're just sitting there. And that's what zero acceleration means. The part that messes with people's brains a little bit is zero acceleration also means constant velocity. And this is the one that people forget sometimes. So, for instance, when you're driving your car and you see the speed limit is, say, 55, well, if you're driving the speed limit, that means you have zero acceleration. If you are driving the speed limit at constant velocity, that means you have zero acceleration. So when you're driving your car and you look at the speedometer and you see it's just sitting there at 55, well, that means you have a constant velocity. You aren't accelerating. And these are the two things, these are the two possibilities. If there's zero acceleration, it could be possible you're not moving. But zero acceleration also means it could be possible you're traveling at a constant velocity. And so it's the second one that people tend to forget. People tend to think zero acceleration means that I'm not moving. Not moving means you have actually zero velocity is what not moving means. And so pair these together means you're not moving, but constant velocity. So velocity can be some value. So this is where velocity is not zero. And these are the two cases I'm trying to stress to you because these are the ones that get mixed up. Acceleration is zero. You're not moving if your velocity is zero. You could also have an acceleration of zero where your velocity is constant, something that's not zero, and you're just moving at constant velocity. And the best example of this is when you drive the speed limit. And that's an example of zero acceleration. And they're talking about here Newton's first law in the book here. And Aristotle, many years before Newton, what Aristotle said a long time ago is when you move an object, it stops. No matter how hard I try, no matter how hard I throw my pen, it'll eventually stop. And Aristotle thought that the universe just stops things. The universe just tends to bring things to a stop. And that was actually one of Aristotle's rules that, hey, look, whenever I slide stuff, it just stops. Maybe that's just the way the universe works, that when you slide stuff, they just stop. And Newton was the one that changed that. Newton said, actually, once you move something, that object will want to stay in motion unless acted upon by another force. Now, the other force in this case we now know today to be friction. But back in Aristotle's time, at least he didn't have that idea that the universe just wanted to stop things. Where Newton's first law says no, actually things want to stay in motion. If there were no forces acting on my pen and I slid it, then it would just want to slide forever. What stops my pen from sliding forever is that there's frictional forces then from the surface that my pen is sliding on. And that's Newton's first law, that an object in motion, that if I have an object in motion, it wants to stay in motion unless some force comes in and then changes that. And that was different from Aristotle, where Aristotle thought the universe just tended to stop things, because it just seemed to kind of be the intuitive answer there. Where I don't think, I'm almost positive Newton didn't come up with the idea of friction, but certainly the one to incorporate that. And I think that's why the first law kind of stands out a little bit today. It's not really in a mass statement. It's more a statement I kind of see against Aristotle that no, objects will stay in motion. An object will stay in motion unless acted upon by a force. And that's what they're trying to talk about in this first section here, talking about pushing a puck, that if you push the puck, just like I'm trying to do with my pen, if there was no friction, then the puck would move forever. And they're trying to show in this picture here, this is supposed to be like an air table, which is supposed to reduce friction. And in an air table, you could push the puck a lot. So if you've played air hockey, you have the little thing you hold in your hand. You knock a puck back and forth. That's air hockey on top of an air table. And the air comes out of the table to try to reduce friction so that the puck slides around very easily. Inertia is what I was talking about earlier about mass. Mass is a measure of your resistance to motion, and that's what they're calling right here. Measure of inertia is called mass. And inertia, our resistance to motion. And I notice they are using R here, so I just want to be clear about this because there is this different terminology. We have this means add all the forces together. Add all forces together. Some people say this equals the net force. Some people will say this is the resultant force, which is what our book is saying here with R. They're calling this the resultant force. And just so it's clear, all those things mean the same thing: resultant, net, sum of forces. And you can see down here in 4.4, they're using the summation symbol. And well, actually, you can see it right here in 4.3. They're saying R equals this summation of forces. So I just want to be clear that these do mean the same thing. It's unfortunate that there's a lot of terminology that means the same thing sometimes, but that's just the way it is. In this last picture, this is something that we're not going to deal with in homework problems at all. It's just something they're throwing out there. But they're talking about inertial frames of reference, that your frame of reference is either constant, like they're showing with the car, or it's accelerating, like the case with the plane. They're saying the plane's accelerating. And we had to do other things for Newton's laws in an accelerating frame. So Newton's laws would prefer to be in an inertial frame, which means constant velocity. Once you're in an accelerating frame, you've got to be a lot more careful with things. But we won't deal with any accelerating frames at all. All our frames are constant velocity frames. So this last part here meant to be just kind of something of interest, but there's no homework questions or anything about that. Just a point of interest they're showing out at you. So 4.3 is actually where we get the first equation. So 4.1 and 4.2, more introductory stuff. A lot of words talking about stuff. This is where we actually get into Newton's second law. It really bothers me when they write A equals F over M like that, because that's not Newton's second law. Do they actually eventually state, here they finally state Newton's second law, The sum of forces equals mass times acceleration. Now they are using the vector notation, so that's what the arrow means. Now it's my history, the way I've been taught, that the arrow is just a half arrow. Some people do use a full arrow though. That's meant to mean the same thing here. So we're not going to deal too heavy with vector notation. We just don't in 111. Neither does the book. You'll see when we get to the homework problems that they don't even have any vector notation in them. So a little bit of disconnect from the text and the problems here with the vector notation. Right here, this 4.8, this is more how we'll do things. So instead of writing a vector notation, what we'll say is we'll sum forces in an x direction and they'll sum forces in a y direction. And then we'll generate two equations, because our sum of forces in the x direction will equal the mass times acceleration in the x direction, and then the y will equal mass times the acceleration in the y direction. So let's give you a quick example. Let's just say that we have I'm pushing a block. So if I'm pushing it, that's a force applied. So if I'm pushing it to the right, it's going to move to the right, which means there'd be friction to the left, because friction always opposes motion. There's gravity on the book, because everything with mass experiences gravity. And the book is in contact with the table, which means there's a normal force. So these would be the four forces if I was pushing this giant book. And then what we would do, and we will do these for the homework problems as we go forward, is we would say, okay, well, what are the sum of the forces in the x direction? So, standard coordinate system. In the x direction, we would have the applied force pushing in the positive direction. The force of friction is pointing to the left, so that gets a minus sign. And those are the only two forces in the x direction. So now that we've summed all the forces in the x direction, Newton says, well, that equals mass times acceleration, the x component of acceleration. And then we would look at the y direction. So we would say sum of forces in the y direction. We've got the normal force up. We got the force of gravity down. Newton says summing the forces equals ma. This is the acceleration in the y direction now. And normally when you push something on a, like if I push my pen, it's not going up or down or falling through the table. So I'm just pushing it, which means in the y direction, acceleration is actually 0 in the y direction because I'm pushing it smoothly. If there was an acceleration in the y direction, that means my pen would like jump up off the table or it'd fall through the desk. So when you push something, there's no acceleration up or down. And so we just indicate with math by saying, well, that acceleration is 0. And so we get these two equations then. We get the acceleration is from us pushing it and friction working against that. And then in the y direction, we just get that the normal force equals the force of gravity. And this is how we'll solve stuff. But the point here was to show you this notation. That was really the point of this, to give you a showing of this notation and how it works in summing our forces. And it looks like they just give some example problems here, which of course you can check out. I will check out the example problems in our homework now, but that's what's left there, to check out some example problems. And 4.4 is now we get to the mass and weight. So let me say this again. Mass, M, is your resistance to motion, but weight is due to the force of gravity. And at Earth's surface, we say weight is mg, where g is the acceleration due to gravity. So 9.8. I just want to say, I notice our book sometimes uses g as 10. That's fine. 9.8, very close to 10. But unless the book states otherwise, I'd stick with 9.8, because you don't want the computer to mark you wrong because you're off by like a decimal place or something. But weight. So let me go back to my list of forces paper. Where is that? Here it is. So the normal force doesn't have its own math expression. It can be many different things. Friction and tension are similar. So this is the one I want to talk about here, gravity, weight. This one always has an equation, and it's mg. So the force of gravity is mg, and this is commonly just called W. I like to use F sub g. I prefer saying force of gravity over weight, just to try to remind people that this is actually the force of gravity, because that sometimes gets lost with the word weight. You know, weight you might think of as, I don't know, like you're too heavy or too thin. You know, weight is like a food, how we look type of thing. And I think that I'm just trying to remind you that weight is the force of gravity. And that's why I try to call it the force of gravity, just to try to put that in your brain, that the weight you feel is the force of gravity. And that is different than mass. So, and some more examples here. Here's where they're using, so here's where they're saying W equals mg right here in equation 4.9, W equals mg. That's a statement right here. And again, that is the force of gravity. They're saying with 4.10 that the force of gravity is always down. I was going to say almost always. It is always down, the force of gravity, because the force of gravity is always pointing towards the center of the Earth. And now the Earth is, for the most part, round. There's a little differences because it spins and whatnot. But gravity is center-seeking, means it's always going towards the center of Earth. And because Earth is round, means that wherever we are on Earth, like I'm standing right here, well, that means that the force of gravity is always pointing straight into the ground. So no matter where you are on the planet Earth, force of gravity is always straight into the ground, because the force of gravity is always pointing towards to the center, and the Earth is round. So, and just to clarify, you know, if the Earth was a square, which it isn't, but the force of gravity always points towards the center. Force of gravity always points towards the center, like that. But if the Earth actually was a square, well, then there'd be cases like right here. If I zoom in on our square Earth right here, then that would mean that the force of gravity would actually be at an angle. If the Earth was a square. One of the reasons, if not the main reason, the Earth is spherical is because the gravitational force is also spherical. So it's the gravitational force that actually forces objects into a sphere. And that's why when you get asteroids, like smaller bodies, they're kind of goofy looking, because they don't have a lot of mass. So the force of gravity still is center-seeking for an asteroid, but because the force of gravity is so small, it's just not really able to shape that into a sphere. But the larger you get with an object, like once you start getting to planets, you know, you're never going to see a square planet. I suppose maybe in some far high-tech sci-fi type of field, like I know in Hitchhiker's Guide to the Galaxy, they showed a few square planets, and those square planets were artificially made. But you know, that's sci-fi stuff. We've never seen a square planet. I don't think we ever will, because the gravitational force is what causes them to become spherical. And is there anything else? Oh, there's a picture of Buzz in a room. I actually like this picture a lot. I have this poster actually in one of my rooms. This because I think that picture is really cool. Just standing on the moon there. And we'll get into some more problems here that they're just giving examples of. And like I said, I will go through the homework problems though, which I will do right now. So in summation, the important things to remember here are that that we're going to be summing forces, and the sum of forces is mass times acceleration. This is Newton's second law. So that's Newton's second law. This is how we're going to generate all our math from Newton's second law. And then these are the forces that we'll be looking at. These 5 forces. The world is more complicated. It is, but we're not going to concern ourselves with that. We're only going to be thinking of these 5 forces, and I strongly encourage you to try to remember that. The world is complicated. We're going to ignore that complication and just deal with these 5 forces. And the last thing I'd have to say that's important to remember are the 2 cases of, so I'm just going back to this picture here, but the 2 cases of zero acceleration. So there's 2 cases of zero acceleration. One is you're stopped, and the other is that you're in constant motion, or you're driving at constant velocity. These are the 2 cases of zero acceleration. It's the second case that tends to be forgotten. So that's why I'm trying to stress this, is it's very common for people to think if you have zero acceleration, then you must be stopped. But zero acceleration also means constant velocity. So this is what I would call my summation. I didn't quite fit it all on camera there, but here are the 5 forces. Gravity is mg at the surface. Newton's second law, summing the forces equals ma. And don't forget, an acceleration of 0 means you could be stopped, or more importantly, try to remember, you could be at a constant velocity. And that's our material for this lecture. Check out the practice homework that I'll work through.